Radioactive decay is one of the clearest examples of how nature can be random on a microscopic level, but still look predictable on a large scale. For a single radioactive nucleus, there is no internal countdown clock telling it exactly when to decay. Quantum mechanics does not give one exact decay time. Instead, it gives a probability. That is why half-life is often misunderstood. Half-life is not a deadline for one nucleus. It does not mean a nucleus must decay by that moment. It means that after one half-life, each nucleus has a 50% chance of still being there and a 50% chance of having decayed. So if one nucleus survives the first half-life, that does not make it overdue. In the next interval, the rule is still the same. Another 50-50 survival test. That is why a single nucleus can survive several half-lives and still behave completely normally. What looks strange for one nucleus becomes clearer when we look at many nuclei together. Now the same decay rule is applied independently to every nucleus in the sample. If the sample is very small, like only a dozen nuclei, the result looks jagged and noisy. Sometimes several decay early. Sometimes several survive longer than expected. Randomness dominates the picture. But when we increase the sample to something much larger, the fluctuations become much less important relative to the total. The randomness does not disappear. It averages out. And that is when the familiar smooth decay curve appears. This is the key idea. One nucleus is unpredictable, but a large collection becomes statistically predictable. That is why radioactive decay is described so well by an exponential law. If we start with an initial number of nuclei, n0, then the number remaining after time, t, follows the curve. N of t equals n0 times e to the minus lambda t. Here, lambda is the decay constant, the probability per unit time that a nucleus decays, and half-life is linked to lambda by the usual relation involving the natural logarithm of 2. A very simple way to visualize this is to represent many nuclei with identical objects, like coins, markers, or random binary outcomes. In the teaching model behind this part of the animation, 200 identical objects stand for 200 radioactive nuclei. At each round, some are removed, representing the nuclei that decayed. When we repeat the process, the number remaining falls in a way that closely follows the expected exponential trend. The exact count changes from run to run, but the overall pattern remains the same. So the lesson is not that randomness disappears in big samples. The lesson is that randomness becomes organized statistically. That is why one nucleus may survive much longer than its half-life, while a large sample still decays exactly as the theory predicts on average. There is also one important quantum nuance. The exponential decay law is the main story for ordinary times, but at extremely short times, the survival curve can begin a little flatter than a simple exponential would suggest. And if measurements are repeated very frequently, the decay can be slowed even more. This is called the quantum Zeno effect. It is a subtle reminder that the exponential law is an excellent practical rule, but the deeper quantum picture has extra structure at very short times. So in the end, radioactive decay gives us a beautiful bridge between chance and order. Microscopically, decay is probabilistic. Macroscopically, decay is statistical. One nucleus is random. Many nuclei reveal the law. If you want, I can turn this into a more dramatic YouTube-style narration, or a slower classroom-style version.